All right, welcome to the Explainer. Today, we're setting the stage for a really fascinating zoom in, zoom out journey. We're going to start big, looking at sweeping global weather forecasts. Then we'll zoom all the way down into the microscopic physics of the ocean's actual engine. And finally, we'll zoom right back out to see how all of this impacts our entire planet.
Okay, let's just jump right into it with a staggering statistic straight from the NOAA's Climate Prediction Center. 82%. That is the probability that a new El Niño will emerge by the May to July period of 2026. Think about that for a second. We are looking at a highly probable, massive shift in global climate patterns that's literally just around the corner.
So, here is our roadmap for today. First, the return of El Niño. Second, unpacking the ENSO climate pattern. Third, the physics behind the oscillation. Fourth, two flavors of El Niño. Fifth, global impacts and weather extremes. And finally, preparing for the future. Let's get into it.
Section 1. Unpacking the ENSO climate pattern. Before we can really decode El Niño, we need to understand the broader cycle it's actually a part of.
You see, ENSO is this naturally occurring climate pattern, and it's totally driven by fluctuating ocean temperatures in the central and eastern equatorial Pacific, which are tightly coupled with the atmospheric changes right above it. El Niño is really just the warm phase of this broader ENSO cycle. Think of the whole thing like a massive planetary pendulum. It swings back and forth every 2 to 7 years between its warm phase, its cold phase, which we call La Niña, and a neutral state right in the middle.
And man, the Pacific has been incredibly volatile recently. We've basically been ping-ponging back and forth. We started with this multi-year La Niña stretching from late 2020 all the way to early 2023. Then, boom, a historic, incredibly strong El Niño emerged across 2023 and 2024. By April of 2024, we swung back to ENSO-neutral conditions, followed by a brief dip into La Niña in late 2025. And now, the data is signaling a rapid shift right back toward El Niño. It is an extremely active period for the Pacific Basin right now.
Now, you might be wondering how scientists actually measure all this. Traditionally, they use something called the Oceanic Nino Index to measure absolute warming in a specific region of the Pacific. But today, advanced metrics like the Relative Oceanic Nino Index, or RONI, take priority. This metric measures relative warming, and this is absolutely crucial because it allows researchers to carefully separate the natural ENSO warming from broader global ocean warming trends. It essentially gives us a much clearer, cleaner picture of the actual ENSO cycle itself.
Moving on to Section 2, the physics behind the oscillation. Let's look under the hood and see how this oceanic engine actually forces that pendulum to swing.
It all starts with something called the Bjerknes feedback loop. First, the easterly trade winds blowing across the Pacific start to weaken. Because these winds drop off, they literally stop pushing warm surface water to the west, allowing all that warmth to surge right back eastward across the ocean. Finally, this warming in the east further reduces the temperature difference across the entire Pacific, which, crazy enough, weakens the winds even more. This loop acts exactly like a battery charging up. As the winds weaken, the eastern Pacific warms, which in turn weakens the winds even more in this continuous, self-reinforcing loop.
And you can actually see this happening deep underwater. Take the evolution of the massive 1997-98 El Niño, for example. Even a full year before the surface reaches its maximum warmth, there is a depression of the thermocline. That's the boundary between the warm surface water and the cold deep water. And it spreads incredibly slowly from west to east. It's kind of like a concentrated wave of heat traveling deep underwater before it finally erupts to the surface in the eastern Pacific.
But, El Niño can't last forever. That battery eventually has to discharge. Scientists actually use 4 distinct models to explain exactly how the ocean forces this termination. The delayed oscillator points to waves reflecting off the western boundary of the ocean. The recharge oscillator describes a massive discharge of equatorial heat. The western Pacific oscillator involves wind-forced waves coming from the west. And the advective reflective oscillator focuses on anomalous ocean currents. While the specific mechanics definitely differ, they all provide that absolutely crucial negative feedback required to shut down the warming and swing the pendulum back the other way.
Section 3, 2 flavors of El Niño. Because, as it turns out, not all El Niños are identical. They actually manifest in a couple of distinct varieties.
There's a really stark contrast between the two main types. On the one hand, we have the traditional Eastern Pacific, or EP, El Niño. This is where the maximum warming is centered way over in the eastern cold tongue, driven by those subsurface waves traveling all the way across the basin like we just talked about. But on the other hand, we have the increasingly common Central Pacific, or CP, El Niño, sometimes called El Niño Modoki. Here, the anomalies are centered much further west, right near the international dateline, and the subsurface warming develops right there in place, rather than traveling across the ocean.
And this spatial shift is a real game changer because it completely changes where the atmospheric heating occurs. Because the Central Pacific flavor has its warmest waters near the middle of the ocean, the massive thunderstorms and atmospheric disruptions happen in an entirely different location compared to the Eastern Pacific flavor. This seemingly simple shift in longitude on a map dramatically alters global weather patterns and what we call teleconnections. Which brings us to Section 4, Global Impacts and Weather Extremes. Let's zoom back out to the macro level to see why these oceanic shifts matter so much to all of us.
An El Niño acts as a massive weather disruptor for the entire globe. It triggers a cascade of very specific extreme events across totally different continents at the exact same time. We typically see increased rainfall and severe flooding in parts of South America. Over in East Africa, it can trigger severe short rains between October and December. Conversely, it causes punishing droughts in eastern and northern Australia, Indonesia, and parts of South Asia by suppressing their usual monsoon activity. Interestingly enough, it also tends to reduce hurricane activity in the Atlantic. It's a true, literal global domino effect.
But we have to remember, ENSO doesn't operate in a vacuum. The World Meteorological Organization put it perfectly when they noted that 2024 hit record temperatures due to a combination of a powerful El Niño and human-induced climate change. A warmer ocean and a warmer atmosphere provide extra energy and extra moisture, and that amplifies these exact extremes we just talked about, making the heat waves hotter and the heavy rainfall much heavier.
Let's move on to our final section, Section 5, Preparing for the Future. Let's look at how the global community uses this incredibly complex data to actually get ready for what's coming.
Looking ahead, the forecast is remarkably clear. The NOOA ensemble models give us a near-certain 96% probability that this incoming El Niño isn't just going to arrive, it's going to persist right through the upcoming Northern Hemisphere winter of 2026 to 2027. For governments and agricultural sectors worldwide, that is a massive, flashing operational signal.
And this is exactly why we track all this math and physics so closely. Improved seasonal forecast models now give us 1 to 6 months of lead time. This is an absolute lifesaver. It allows organizations like the WMO and local governments to impartially activate emergency protocols, adjust agricultural planting schedules, and pre-position humanitarian supplies way before the extreme weather actually hits. It literally translates complex ocean physics directly into saved lives and protected resources. Now, beyond these rapid year-to-year swings of ENSO, there's one more piece to the puzzle we have to consider: PDV, or Pacific Decadal Variability. Think of this as the background music. It's a decades-long rhythm in the ocean that looks a lot like a broadened ENSO pattern. Depending on whether this long-term decadal background state happens to be warm or cold, it can actually dampen an individual El Niño, or it can totally supercharge it, altering its impacts all over the globe.
Which leaves us with this final, absolutely critical question to track as we watch the weather data unfold for the rest of 2026. As the Pacific's engine charges up right now, how will the background rhythm of Pacific decadal variability, combined with overall global ocean warming, interact with this impending 2026 El Niño? It's an incredibly complex puzzle for sure, but thanks to this data, we are better equipped than ever to understand it and prepare for it. Thank you so much for joining me on this explainer. I'll see you next time.